Hello everyone, my name is Anton Pelcher. I'm an engineer and I build fish farming facilities for over 10 years. Today we're going to talk about an aeration field. What is it really and what is it used for? Let's start with some basic things. Fish, in the course of their life processes, consume oxygen and release carbon dioxide. So this carbon dioxide tends to accumulate in the water, meaning it builds up in dissolved form in the water of your RAS, Recirculating Aquaculture System. In flow-through farms, this problem hardly ever occurs. It's mainly an issue in closed systems. So, it accumulates in your system and it needs to be removed because fish are sensitive to carbon dioxide. Yes, there are species that are less sensitive to it, for example African catfish and to a lesser extent sturgeon, but cold water fish species such as trout and whitefish are very sensitive to carbon dioxide, so it's essential that its concentration in your system does not exceed about 15%. This carbon dioxide, measured in milligrams per liter, needs to be removed somehow. And now, if I ask those who are already more or less familiar with fish farming and how RAS works, I would ask, what is degassing and what does a degasser actually look like? I think that at least 8 out of 10 people would tell me, well, it's a big tank. In this tank, there are bioblocks or some kind of buffel plates installed inside, water is supplied from above, everything is sprayed around, maybe a fan blows in, blowing out the carbon dioxide, and overall, yes, you would be right. But this is not the only device used on fish farms. For water degassing, there is a device that doesn't lift anything anywhere, doesn't spray anything anywhere. It works right in the reservoir where, for example, your water flows. Yes, you heard that right. If you're interested in learning about such a system, give this video a thumbs up and let's get going. So let's start with some basic numbers and see how much carbon dioxide is produced. Let's imagine we have 10 tons of fish in the system. How much carbon dioxide will these fish produce? I'll grab a calculator to help and we'll start counting. Let's take, for example, 1.5% of feeding per day. Let's assume that we already have more or less market-sized fish. That's 150 kilograms of feed. These 10 tons of fish consume that amount of feed per day. For every kilogram of feed eaten, the fish consume about 300 grams of oxygen, which is 45 kilograms of oxygen. That's how much oxygen your fish consume per day. For every kilogram of oxygen consumed by the fish, about 1.4 kilograms of carbon dioxide is released, which means 63 kilograms of carbon dioxide. So every day, that's how much is released. We multiply this by 1,000 to make it clearer and then divide by 24 hours. So that's 2,625 grams, to be exact, of carbon dioxide your fish release per hour, and all of this dissolves in the water. And these 2,600 grams per hour, essentially, we need to remove using degassers. Now let's talk about how degassing actually works. In fact, it's all very simple. Water that is in this atmosphere without any external influence will indefinitely maintain a normal gas composition. It's always the same. Most of it is nitrogen, but it also contains oxygen and various other gases. When something affects the water, like pressure, aeration, or oxygen saturation, this normal gas composition gets disrupted, and that's where degassing comes in. Essentially, it's designed to restore that normal gas composition. So how does this actually happen? The thing is, we can't just leave water in the system's components. To allow it to contact the atmosphere indefinitely, we need to remove the gases from it here and now. So, to do this, we speed up the process using degassing. Here's what we need to do. We need to maximize the surface area of contact between air and water. There are two main technologies for this. And the first technology, which I already mentioned briefly, is water spraying. Basically, all degassers work to spray the water. That is, the water is lifted up into a kind of tower. Inside the tower, there are all sorts of different deflectors. These can be plastic bioblocks, various perforated partitions, or something else. Anything that helps break the water up into droplets as much as possible, because then each droplet has a much larger surface area in contact with oxygen than if you just had all the water together in one mass. If we talk about the second technology, it's not the mountain going to Muhammad, but the other way around. In other words, we introduce air into the water instead and create the process inside. With the help of bubbles, we maximize the contact area between the atmosphere and the water. The aeration field is actually a pretty simple thing. The most important thing is to choose it correctly. At a depth of about 70 centimeters from the water's surface, an entire field of perforated pipes is installed. Usually, PVC pipes are used. They are placed on a stainless steel stand or secured in some other way so that the airflow doesn't tear them out or lift them up and so on. They are perforated and compressed air is supplied to them, usually from a high-pressure fan or a vortex blower. And so we have a large flow of air going to these diffusers. They generate a huge number of microbubbles, which rise up and accordingly carry the carbon dioxide away with the bubbles into the atmosphere. So essentially we create a large aeration chamber. This is what is called an aeration field. That's actually its name. Let's talk about the advantages and disadvantages of the aeration field. In general, where can it be used, where can't it, where is it good, and where is it bad? Let's figure it out. So the first advantage of the aeration field, it doesn't take up any extra space. The aeration field is simply integrated into the channel. Sometimes, of course, a separate chamber is made for it, but in fact it can be placed anywhere there is enough space and where water flows. As a rule, this is already at the end of the system, right before the airlift and before pumping with pumps. That's one of its advantages. The second advantage is that there is nothing there that can break. That is, yes, of course, you have a fan or a blower located in the compressor room which could break down, but if you maintain it properly and it's of good quality, nothing will happen to it. From this blower, a pipe runs, and down there's a stand, a partition, and perforated pipes. They don't require maintenance, they don't break down, nothing happens to them at all. You can simply turn on the aeration, it works, it bubbles, and you can turn it off whenever you want. So nothing overflows like in a regular classic degasser, and that's an undeniable advantage. Now let's talk about its disadvantages. Well, the first disadvantage is that it's comparatively larger energy consumption compared to a classic degasser. That is, if we supply a classic degasser carefully with a very low pressure pump, which is quite efficient, for example, a propeller pump, then if we compare the two, it turns out that aeration systems are less energy efficient than a classic degasser. Well, actually, in my opinion, that's where the disadvantages of aeration fields end. Although, by the way, there's one more. If you have a classic RAS farm and there are no open channels or free space where you can install this aeration field, then yes, it will require a separate sump. Of course, this is also something that needs to be taken into account. Now let's talk about selecting an aeration field. Let's skip all the complicated scientific formulas. Honestly, I really don't like that. I have a straightforward engineering approach. So how would I make an aeration field? How do I do it? The first key figure is the air-to-water ratio, the aeration coefficient. That is, if 1,000 cubic meters flow through your aeration field per hour, I would use a 5:1 ratio. I always stick to this for the aeration field. So 5,000 cubic meters of air per hour, that's what I would supply to this system. Yes, that's a lot, but that's what's needed to blow off the carbon dioxide. That's what I was telling you about. It's a relatively high electricity consumption. The second point is the depth I would set. I would install the diffusers at a depth of 70 centimeters. That's the standard installation depth. Anything deeper results in higher energy costs, and anything shallower means less efficiency and less rational use. Very low. The last point I want to mention regarding selection is that I would recommend high-pressure fans. They are the most energy efficient and cost-effective for these kinds of tasks. If you can't find high-pressure fans with the required efficiency and price, you can easily use vortex blowers, which are widely available on the market. Let's talk about the air supply duct. I would make it with a diameter that allows for an air velocity inside the pipe, 8 to 10 meters per second. This is the optimal range where you don't have excessive pressure losses. And at the same time, the pipes and fittings aren't too expensive, because large valves can be quite costly, and all of this is difficult to install. As for the diameter of the perforations I would make, your diffusers are about 4 to 6 millimeters. And finally, let's talk about where I would install the aeration field. As a rule, I install it at the very end of the entire system, that is, after mechanical treatment, biological treatment, and after the sinking filter. Only then do I install the aeration field before the water reaches the airlifts or the propeller pumps, in other words, almost at the end of the cycle. Well, that's basically everything I wanted to say about the aeration field. I hope you found it useful. If so, give it a thumbs up. Subscribe to my Telegram channel. Check out this video. This was Anton Pelcher and my channel about how to grow fish and make good money from it. Bye-bye.